In this video we will construct a Merkle tree from scratch, and we will use a Haskell for this. So let's say about what is a Merkle tree. A Merkle tree is a very popular data structure in the blockchain world. For example, in Bitcoin it used to prove that transaction is inside some block without having the entire block. So actually we know the Merkle hash, and we have some transaction and the access to some trusted node, and this node provides to us the Merkle path. And using this information, a Merkle path, and the available Merkle root in the network, we can prove that this block or transaction inside the block. Okay, how we construct a Merkle tree? For example, if they have some transactions, you can see here at the bottom level. Actually, at first you have the list of transactions, and this and they form some block. So here we have this block of transactions from 7 to 40. And first thing you do is you take the convert these transactions into their hash, and actually this is the lowest level. Also, you need to make this list the even length. If it is not even, just duplicate this last element here. When you concatenate this, group this lower level by pairs and concatenate them and produce a new hash here of this concatenation, of this leaves concatenation. And then you go to the little and then you repeat the iteration process. So you go to the level up and do the calculations of the children's, of the concatenations of the hash children's, and so on until you build a Merkle root. So actually this is the main logic, and let's implement it in Haskell. So I have these two imports here. The first import which contain this data type of the binary tree. So how we define the binary tree? Actually, the Merkle tree is a binary tree, as you can see here, and this is either empty tree or some node which consists from the node elements and the two trees, left and right trees. Okay, and also I will use this simple hashable module here. I don't want to use SHA-256. I will simplify a little bit these things, because I don't want to install this library, and Haskell has this library. Let's look how it works. So we can import this module, and now we have a hash function which takes some hashable and produce an integer. So for example, I can take a hash of this string, and I will receive this hash, and I will use this hash to build the Merkle tree. But of course you can change this function to the SHA-256. Okay, and the first thing I want to do is to create simple function, because I want to take some strings as nodes of my binary tree and produce a new strings as a hash. But here I have the integer and I need to change it, so I will write a simple function which just use this function and transfer it into the string. Okay, so Actually, this thing will give will have the type from string to string. Okay. What I want to do next? Next thing, I want to build the Merkle tree, and to do this, I need to define some function which I call Merkle, and its type signature is it takes the first hash function. The first argument is hash function, which is used for hashing. The second function is actually the list of string, which this list contains these lowest levels. Actually, this is transactions from Bitcoin. If how Bitcoin it is used, it uses a list of transactions here. Okay, of course we can have any other strings. This is the data blocks, and they produce a binary tree of string. Okay. Okay. And of course, we will use some helper function for this. As always, okay, we need to define at first the arguments, name the arguments. The first argument is our hash function, and the second argument is our data list. And we will use the go function helper, which will implement our iteration process. Okay, and we need to provide for this helper function the new list. Actually, we need to build a new the list of hashes. Okay, of course we can do this very simple using the fmap function. We can map our data elements to the hashes. Okay, and let's write type signature. So actually, for this function go, let's define it. Actually, what did they take on input? I say that I will give the list of hashes, but as you can see here, we represent our binary tree like this. And actually, it is will be easier if I provide a list of nodes which represent the leaves, and then the will collapse this list to the list of the same type. But on every step, the number of elements will be divided by 2, and at the last step, we will finish with our root. Okay, and this means that we have a binary tree of string list, this list, and produce at the end we produce the full binary tree of our hashes. So we end with the Merkle root. And let's define this initial argument here. So as I said, the first we need to construct a list of nodes, and they construct it from our initial data. So not actually the initial data, they construct it from a list of hashes. So at first they need to build this list of hashes, and then we will use it to produce this list of nodes. Okay. So actually here I construct a node of this hash of n. The n is our transaction, and we have the two empty left and right subtrees because this is the initial leaves. Okay, and here I need to define this this name, and I defined it as so I need to transfer my initial list of transaction into list of hashes. and this list also must be the even length. And of course I'll check for this here. If our list have the even length, our initial list have the even length when they use the list as it is, but otherwise they need to modify our list. They need to take the last element and add it to the end of our list, and we do this with this expression. Okay, this will give us the even length, so I can call it even data, even data. Okay, now when the here have this even length list, what we do next? Next, this list goes into our iteration process, so we must to define our function which take this node list of even length. And how we defined it? Of course, this is the recursion here. We run our go process again, but they need to somehow compress our list. So on every step we divide it by 2. And how I do this? Of course, at first I need to group my list into sub-lists which contains the 2 elements, the 2 nodes. And after I do this, I can fmap these pairs into the one node, and this will give me the result, the list of nodes which I expected. And how to split a list of some elements into the list of parts, into the list of lists which contains 2 elements. So somehow to split into parts by 2. And we have very nice function for this. It calls chunks of function. Chunks of. Let's look at its type signature. So I think I need to import module for this function, and this module is data list split. So let's import it. Data list split. Okay. Now if I import this module here, I can show you the type signature of this function. As you see, I need to provide the integer, so this is the length of the group, of the splitting groups, and I need to provide the list itself. So as I said, it takes this list, initial list, chunks by 2, and then the take every element. Actually they do f mapping here. So we take every element, every group of this list. Now I can unpattern match these elements, because I know here that they have we have the pairs in our list, so each list consists of 2 elements. So having this information, I can unpattern match each element. And let's do this here. So actually I want to construct a new list here. Okay, I do unpattern matching. We have some node 1, node 2, and the empty node. Okay, so this is our unpattern matching. And from these 2 nodes, I want to build a new node. But to do this, I want to somehow dive into these nodes. Also, of course, I will use unpattern matching here for this n1 and n2 because I want to extract their hash values. Okay, and how I do in pattern matching, I'm use them for this n1. I can and pattern match it is with a node constructor of my tree. So we have this tree, binary tree, and I want to extract the node 1 value. Actually, this is the hash, and I know I'm not interested in the left and right subtrees. I just want these hashes. And also we do this for this node 2. This exactly the same in pattern matching for node 2. And what we build here? So we build here some new node, and they need to provide for this node the new hash and the new left and right subtrees. And of course this new left and right subtrees will be these two nodes. Okay, and I just provide them here. And here I need to construct the new hash. Of course, for constructing a hash, I have this function hash, which I defined here, and I need to provide some string. But this string is built from concatenations of the subnodes. So I need to implement some concatenation function. I will call it C at this moment. And I need to provide the hash of the node 1 and hash of the node 2. Okay. And this will build me the list of the length divided by 2. So actually I do one step of iteration and I can go repeat my iteration process here. What I need to do here next, I need to define my concatenation function. So how I do the concatenation? We take two values, value 1 and value 2, and our concatenation actually is just the string concatenation. Okay, so actually I can let's say it like it is, because maybe we want to change this. Okay, and last thing we need to do is to build our base case. So what is a base case? The base case, then they have a list which consists only from 2 elements. If they have only 2 elements, actually we can stop. Because we can build a root and return it. Okay. So how we in pattern match the list of the 2 elements? It in pattern match like this. So we catch this case like this pattern. And of course I need to dive, as I said, as I do here, inside these nodes. Actually I can just take these patterns, 2 patterns here, and put them here. Okay. And what I need to do, I need to produce a new node. So actually I need to do the same thing like this, without do any repeating of my iteration. So this is actually the base case of my recursion. Okay, and I think that's all. We can try to compile this. Okay, let's run my GRCI again. Let's load my file. We have actually, so I can define it actually like this. I think like this. Okay, conflicting. Of course, here I need to use N2, and we do our compilation, and let's try to build a Merkle tree with my hash function and with a list of some transactions. For example, I will identify my transaction data as 1, 2, 3, 4. Of course, real transaction data is have much more data, but here for simplicity I use this information, and we have see this construction, and of course I will print my Merkle tree. So you can see this list of hashes. Actually, this is the Merkle tree. This is the leaves. This is the A. Sorry, this is the 1, this is the 2, this is the 3, and this is the 4. Actually, this is hashes, and they built it until the root. Of course, in the Bitcoin used SHA-256, but here I use a simple function. You can replace it if you want. You just need to install some modules which provide this function. But here is the logic which is used to build this Merkle tree. Okay, and in the next video I will implement the function which allows to check at first it will build the Merkle path or authentication path, and then we will check that some transaction inside our block. We will implement this logic in Haskell. So guys, thanks for watching. Push like button, push subscribe button, and see you in the next video. Bye bye.